Okay, welcome back to my next video. What we're going to be doing today is we're going to be working through still working through uh, Unit 20, which was the HL organic chemistry section. Organic chemistry section. So we've already covered like reducing agents. We've already covered reducing carboxylic acids to aldehydes and alcohols. And we also reviewed oxidizing alcohols to aldehydes and carboxylic acids, and same thing for ketones down to secondary alcohols or tertiary alcohols. So yeah, we've already covered almost all of that. So what we're going to be doing over today is just a little bit of synthetic routes. It's kind of like a compilation of everything you need to know for forming a final product. So basically, we're going to go through the steps. These steps are outlined in your textbook. So if you've got your textbook, just read through that, and then watch this video. And hopefully, this video will help you to know how to answer these type of questions. So basically, just to start off, let's say step one. So we're gonna have a four-step process, and step one is just determine your starting materials. So determine, and the question will typically give you this: determine the starting materials. So when you determine the starting materials, the question will say, okay, this is what you have. So always try to draw out your starting materials and know what the stereochemistry is of your starting material. Know what type of reactions it undergoes. And then also the question should say, what is your desired final product? So what is the desired final product? And the most important thing for both of these, I'm going to write it in red over here, is you must focus on functional groups. So you must focus on the functional groups. You have to focus on, as we said, functional groups. Those are reactive groups. So by knowing your functional groups, you know what type of reactions they undergo. So we're going to see that by the end of this video. So step two is you should consider reactions that can lead to the final product. Can lead to final product. And you want to do this from both ends. You're going to have your starting material. You're going to have your final desired product. And it's a good way to solve this is your starting material. You can say, okay, what reactions can my starting material undergo? And what reactions can my final material undergo? Because any oxidation, we can undo that oxidation. Any addition, we could undo. So we can anything that's oxidation reduction, we can go from our final product back to our starting product. Any addition reaction, it's easier to go from your starting product to your final product. So you want to start solving, which way is the best way to work, and then what products are in the middle, and then how can we convert these two products in the middle into one another. So basically we can start to plot out what reactions your starting product can go through and what reactions your final product can go through. So basically you start to plan the path, and you need to look at it from not only one direction, but you want to look at it from both directions, kind of like a build-up direction and a breakdown direction. So step three is kind of consider reactions that can lead to the final product, or vice versa, and then consider how to convert between them. So this one, you could just say, okay, well, we end with an ester, so we know esterification. So we know we need an alcohol, and we know we need carboxylic acids. So we know we need these two. Then you could say, okay, well, alcohols are pretty easy to get. We just need to have a hydroxide and react it with a halogenoalkane. Whereas carboxylic acids, we can take a primary alcohol and we could oxidize it. We can just oxidize it to a carboxylic acid. So there's multiple ways to get through this. So basically, how can we convert between the starting product and the final product? And the last step, step 4, is basically just designing a pathway. Design a pathway uh, with, and what I like to say, minimal steps and time required. So to design a pathway with minimal steps and and basically with minimal steps you minimize the time. So basically you minimize loss and you minimize the time it takes you to do the reaction. So if you imagine, synthetic steps are not always efficient. If you imagine we did, let's just see, let's just say we had primary alcohol. We've got ethanol here, and we want to make ethanoic acid. Let's go through a two-step process. So we're using K2Cr2O7 in an acid. So potassium dichromate, we're using that in sulfuric acid because this acts as a catalyst to oxidize it to an aldehyde, OH. Sorry. 1, 2, 3, 4. Good. 1, 2, 3. And finally, to our carboxylic acid, using the same thing, K2Cr2O7 in H2SO4. So you imagine these two reactions, and maybe this process is only 80% efficient, so we've already lost 20%. So we lost 20%. So we've got 80% of the aldehyde, and say this is only 80% efficient. So 80% of 80% is going to be a 16% loss on top of this. So instead we've got a 16% loss on top of the already 20% loss. So we're just going to lower the amount of product we have each time. If this conversion is only 80% efficient, we're only going to get 80% of the 80%, which means that we're going to end with, like I said, 16% loss. So we're going to end with a 64% conversion efficiency. So we started at 100%, and to get to the final, we've only made 64%. So we've went through 2 steps, and we've lost some. If we want to minimize the steps, so if we minimize the step, right? If you remember the other oxidizing agent we have, let's erase this off here. Like I said, we had a strong oxidizing agent. We didn't need to use potassium dichromate. We could use potassium permanganate. So we could just use KMnO4 in an acidic solvent, and we can go in one step to carboxylic acid. And imagine this is 80% efficient. Now we've got 80% versus 64% of our product. So we've increased the efficiency by decreasing the steps. This may not be true in every circumstance, but typically minimizing steps, you minimize the loss. So that's basically why we want that step 4. We want to minimize the loss of products. So let's do an example of this. Let's do an example. And this example is in your book, but I'm going to walk you through it just a little bit more. So we've got chloromethane. Chloromethane. If you don't know how that looks, it looks like this, except for this is a tetrahedral. Hopefully you remember. Tetrahedral structure, 109.5 degree difference between all of them. And our final product, so we're going to work through this. Our final product, we want ethyl methanoate. So we want ethyl methanoate as our final product. So how to draw that out? If you forget, it's COCC. So that's ethyl methanoate. So we can break this up into what we'd need to react to form it. So let's see, ethyl methanoate. I'm just going to erase this and move this structure up a little bit. So basically, our starting product is chloromethane, and our final product, I'm going to draw it a little bit smaller, ethyl methanoate. I'm just going to make sure this is still recording. Okay, we're good. Ethyl methanoate. So that was COOCC. And anytime I don't draw what's at the end of the bond, I'm just assuming it's a hydrogen, or you can just assume it's a hydrogen. So ethyl methanoate, we know that this is an esterification. This is an ester. So if you don't know that, you need to go back to Unit 10 before going over Unit 20, because they all build on each other. This is an ester. An ester is formed from the reaction between an alcohol and carboxylic acid with an acid catalyst. So with an acid catalyst. So the alcohol is always the end that's single bonded to the oxygen, and the carboxylic acid always maintains that double bonded oxygen up here. So this is going to come from methanoic acid, and the alcohol is going to come from ethanol. So now we've got methanoic acid and ethanol. We start with chloromethane. So, we've only got one carbon here. IGCSE doesn't need you to learn any reactions that you add carbons. So we can't form ethanol. We cannot form ethanol from chloromethane from the reactions that we know. So we know that ethanol is probably just a product we're going to have to add in afterwards. But methanoic acid, right? Methanoic acid, we could see, okay, well, we've got chloromethane. How can we make carboxylic acid out of this? We've talked about nucleophilic substitution reactions. So we know we can add a hydroxide in here to replace the chlorine. So this is me just kind of thinking out loud. So now we've got carbon with hydrogens and a hydroxide. And we know we can oxidize this. We know we can oxidize a primary alcohol to a carboxylic acid, to methanoic acid. So we're already starting to solve the steps. We can just add ethanol. Ethanol is a pretty basic reactant. And we can make methanoic acid out of chloromethane. So this is what we're doing. We're determining our starting materials, chloromethane. We know the desired product and ethanol. Our desired final product, ethyl methanoate. Consider the reactions that can lead to this final product. We broke up the esterification reaction. We've broken it up into alcohols and carboxylic acids. And we've understood that chloromethane can lead to a carboxylic acid through the substitution reaction, through an SN2 pathway substitution reaction with hydroxide to form an alcohol, and then we can oxidize that to methanoic acid. Now we've figured out how to convert between the final things, and then we want to do it in minimal steps. So let me erase all of these steps. Hopefully you've got that written down already. If not, you can of course pause the video and write it down. And then let's work through these pathways. Let's work through what is going to be expected of you for this for synthetic routes. So like I said, if you don't have a good understanding of Unit 10, then you need to really go back through Unit 10. So let's see. I'm just going to erase all of this. I may as well, and then we can work through the steps. Okay, so that's nice. So we had chloromethane. So we got chloro, carbon, and methane. Chloromethane. We've already summarized the steps. Chloromethane, and we want, it was, I believe, ethyl methanoate. So ethyl methanoate. which was CCOH. So that was our ester. I'll draw it out nicely, even with the H's. I'm spoiling you guys. Oh, look at that. Mr. Featherstone drew H's for once in his life. So, okay. So, and we already talked about the steps. So this one was an esterification. So we needed ethanol, which is written ETOH. And we needed a methanoic acid. So you said that ethanol is a typical starting product or a typical reactant. So we've already got ethanol in the lab. You just assume we already got ethanol. But then methanoic acid, maybe we don't have any of that around. So let's work through. Of course, the question would have to be a lot more straightforward and tell you what reactants you have. And if you don't have if it doesn't say you have the reactants, you can kind of assume that you do. You know, you can't just assume you've got methanoic acid, ethanol. Maybe it could say something like, you know, how can you convert this into methanoic acid in order to form this final product with ethanol? So let's go through the first step. We wanted to turn this into an alcohol. So to turn it into an alcohol, you need water and you need a hydroxide. So basically from this, you're going to have, we need a hydroxide, so we can just say maybe sodium hydroxide dilute, and that should be it. Dilute means as dissolved in water, so we've already got water there. So then the water, right, we said SN2 is going to cause that conversion of the structure, and this is a primary halogenoalkane, so it goes over the SN2. So this hydroxide, this oxygen, remember it comes in the back and donates its electrons to the central carbon, and this chlorine takes these electrons, and it's a better leaving group. It's a better leaving group, and hydroxide is a better nucleophile. So it leaves as chlorine minus, and the hydroxide attacks, and instead we get the structure of carbon. The hydrogens are now pointing the opposite direction because we underwent the stereochemical conversion, and we've got the hydroxide here at the bottom now. And then now we've got two options, right? We can oxidize in two different ways. We said we can oxidize either in K2Cr2O7 in an acidic medium, so this is unit 10, or we can do it with potassium permanganate in an acidic with concentrated sulfuric acid. But we had said that, let me just remind you guys down here, K2Cr2O7 is a soft oxidizing agent, and KMnO4 is a hard oxidizing agent. So hard means that it'll oxidize this alcohol directly to a carboxylic acid, and soft means that it'll oxidize this alcohol to an aldehyde in this case, aldehyde, and then we'll have to oxidize it again, KrTr2O7 in H2SO4 in a reflux, and then finally we're going to get the carboxylic acid product. But you see that's one step, two step. Here we've got one step, so this path is garbage. We want to minimize the steps. So let's minimize the steps. Let's use a stronger oxidizing agent in order to oxidize this hydroxide to methanoic acids. Now we've got COOH with the H. Now we've got methanoic acid. So that's one of the things that we need to make the ethyl methanoate. And the last thing that we needed is we only needed to react it with ethanol. So let's erase this. Our last step to our final product is ETOH. That's short for ethanol. F with OH showing that it's an alcohol. F all ethanol. And we need a sulfuric acid catalyst for this one too. We just need an acidic environment. This acidic environment, and this one we also need a concentrated sulfuric acid catalyst with ethanol, and we form the final product. So we can see this is the stepwise procedure. Now, if we wanted to work backwards, right? We can also work backwards. We can say, let's just go backwards from the methanoic acid, because this one we don't know any reactions to undo an ester. So that's the end of that question. So I'm just going to erase the ester here. And let's say, your starting product is methanoic acid, and it says, how do you get to the alcohol? We didn't learn how to interconvert between a hydroxide to a halogen, but we learned how to convert from a halogen to an alcohol. So we're just going to stop there. We don't necessarily need to know this part because it's not in your syllabus. Eventually, when you hit Uni 1, University 1, Organic Chemistry, you will learn all of these reactions. But at this point, you don't need to know that. So let's say we're going to convert between this carboxylic acid to a primary alcohol. I'll erase this, and we're going back the other way. So now we've got, let me just draw the methanoic acid over here. OH, H, double bonded there, single bonded here. There we go. And now we want to convert back to a primary alcohol. Remember, we had two reducing agents. I messed up in the last video, so if you look over it, this is going to be my correction. I wrote sodium aluminium hydride, but it's not that. It's lithium aluminium hydride. So if you go back to the last video, just ignore the sodium, because I messed that up because it was sodium borohydride, which is right, and then lithium aluminium hydride, which is right. And we had done the same thing. We had said that lithium aluminium hydride was a hard reducing agent, and sodium borohydride was a soft reducing agent. So in this case, right, we've got something that, we had said, yeah, this one could reduce ketones, and it can reduce aldehydes, but it can't necessarily reduce carboxylic acids. We can, but again, we need reflux, we need 2 steps. So it's worse. We want to use this mainly for ketones to aldehydes, ketones to alcohols, and aldehydes to alcohols, where we want to use lithium aluminium hydride if we want to reduce a carboxylic acid all the way down to an alcohol, because it was a hard reducing agent. So right, this is sodium borohydride was 2 steps, and we needed the reflux, so we need more time. And the lithium aluminium hydride was 1 step, and it was just a faster reducing agent. So we have lithium aluminium hydride. I like to just write red beneath it to show that we're reducing it to the alcohol. So you can see we can kind of work in both directions. Okay, I'm going to do a quick last summary here. And then we're all done. Or actually, I'll do that in the next video. I don't want you guys to be just staring at the screen watching this one video the whole time. I'll do a second video for all of the reactions that we have to know, and all the reactions that we have to, basically all the reactions we have to undergo. So okay, I'll see you in the next video.